Hello and welcome to this another project tutorial for data science. In this tutorial, we'll build our small automatic credit card approval predictor using some machine learning techniques, just like the real banks do. So we'll go through the entire process that the banks take to, you know, uh, for the decision making for which credit card applications to approve and which ones to reject. This might be something new to you, and I can assure you that we'll learn a lot across our way. Let's get started. So first, what are credit card applications? What is the decision making process behind this, and how basically the banks make this decision which applications to approve and which ones to reject? So commercial banks receive a lot of applications for credit cards, and many of them get rejected for many reasons. And some of the reasons can be high loan balances, low income levels, too many queries on an individual's credit report, for example. So this task is very time consuming as they receive a lot of applications. So we'll try to automate this process using machine learning and data science. So I have used this credit card approval dataset from the UCI machine learning repository. You can see the link on the bottom left. And I'll anyway be putting the link in the description. So this dataset is from the UCI machine learning repository. The structure of the notebook is as follows. First, we'll start with loading and viewing the dataset. We'll make some important observations and not important observations. We'll just make some observations. We'll just see how the dataset looks like. Although the dataset is anonymized for privacy purposes, that we'll still try to get insights from what the data actually looks like. Next, we'll see the dataset is a mixture of both numerical and non-numerical features, and we cannot work with this data at this stage. So another part is that it contains. Okay, I'll better not click anywhere. So next we'll see that the dataset is a mixture of both numerical and non-numerical features, which contains values from different ranges as well. So we need to normalize, we need to convert the non-numerical features to the numerical ones to make to be able to make some calculations. So all this comes in the part of pre-processing, data pre-processing, and we'll see how we do the data pre-processing. Now we'll have to pre-process the data to ensure machine learning model we choose can make good predictions. Now after our data is in good shape, we'll do some exploratory data analysis to build our intuitions. Intuitions are a very important part of data science. So you need to be able to understand your data and have some intuitions. This is my advice. Okay. Next, finally, we'll build a machine learning model that can predict if an individual's application for credit card will be accepted. Okay, so let's go. And we'll first load and view the dataset. We'll find that since the data is confidential, the contributor of the dataset has anonymized the feature names. So as you know how we'll read the dataset, it's pretty simple. We'll just import pandas as PD, and CC apps is the name of our data frame, which will store our contents from the CSV file, which has our data set. So it's not CSV, it's .data. Either can work. So CC apps.head, this helps us in viewing the top 5 rows of our data set, just to be able to become familiar with what our data set is, how does it look like, and this is quite important at some times. Okay, don't get your wires crossed if you cannot understand what this data means. So even I cannot kind of find out what BAABV means, what these numbers are, what are these ranges, what does UG, WV, and T, and all this FG, what does this mean, what is plus, minus. Although I can find out what plus minus is, since this is the last attribute. So this got to be our target feature, which is whether the application is approved or not. However, here's some more information which will help us in inspecting the applications and studying this data set. So the output may appear a bit confusing at its first sight, but let's try to figure out the most important features of a credit card application. So features have been anonymized, but This habit of mine of selecting some text to put emphasis on this while recording the screen is this gotta leave me soon. Okay, so the features have been anonymized, but there's this blog which gives us pretty good overview of the probable features. I'll put the link to the blog in description. Now, the probable features in a typical credit card application are gender, age, debt, marriage status, bank customer, education level, ethnicity, years employed, prior default, employment status, employed or not, credit score, driver's license, citizen, zip code, and income. And finally, approval status, whether the application is approved or not. So this gives us a pretty good starting point, and we can map these features with respect to the columns in the output. Now, as we can see from our first glance at data, the dataset has a mixture of numerical and non-numerical features. This can be fixed with some pre-processing, but before we do that, we'll learn about the dataset a bit more to see if there are any other issues that needs fixing. So, CC apps description is another data frame which, sorry, not data frame, it's a variable which stores CC apps.describe. So when we describe the data set, this gives us some information like mean, standard deviation, minimum, 25%, 50, 75, maximum for different attributes. So this gives us the data for 4 attributes, which can, this gives us the information that we have only 4 columns which are numerical. And these are the accounts and means and everything. We have printed the CC apps description, print new line, and CC apps info will give us some information about the data, like about the data set. So this tells us that total 16 columns, and you have total 16 columns in this data set. And say this is 0th index column. It has 690 values, is completely non-null, and the type is object. So we can see from the data set that the type is BAA. So this is object type, and this first one is of numerical type. So this will be listed here. First one, 690 values, non-null, object type, and second one is float type. I'm so sorry. So this is also saved as object type and not numerical type. So take an example. I'm not sure what is there in this column, what this actually means, and why it is object type and not integer type. But for example, if you're storing zip code in a column, so what will you prefer to storing it as, like as an object type or as an integer type? So if we store it as an integer type variable, it will not be of any use to us to look at the mean, median of the zip code numbers. So we'll choose object type over integer type, because we'd rather want how many of these objects are same, like how many of our entries are from the same zip code. So this might be something like this. We'll get to know this in later. Okay. So next thing we have, we just printed so we just printed cc apps.tail17. So what does tail17 mean? This means that we are trying to print the last 17 entries of our data set. Had we written head 17, so it would have printed the first 17 entries. So here are the last 17 entries. As we know that the number is total 690 starting from 0. So these are all our last 17 entries. And do you notice something here? What's this? What's this question mark? This means missing value. So our next part concerns with handling the missing values. Sorry. We have uncovered some issues that will affect the performance of our machine learning models if they go unchanged. So our data set contains both the numeric and non-numeric data, specifically the data that are of float, integer, float 64, int 64, and object types. Now, specifically, the features 2, 7, 10, and 14 contain numerical values, as you can see here. Yeah, 2, 7, 10, and 14. All these are float value types. So this is what I'm talking about below. Yeah, float, integer, and object types. I'm sorry. Yeah, 2, 7, 10, and 14 contain numeric values of types float 64, float 64, int64, and int64 respectively, as we saw. And all the other features contain non-numeric values. Now, the dataset also contains values from several ranges. Some features have value of range 0 to 20, some have 2 to 67, and some have this high range. So what we want to do is to normalize them and to kind of store them in within the same range for us to be able to make some calculations easier, more in an easier way. Now finally, the dataset has missing values which we'll take care of in this task. Missing values are labeled with question mark, which can be seen in the last cell's output. So this is the last cell's output, and we can see this question mark here. Let's temporarily replace these missing value questions with question marks. Missing value question marks with NaN. So what NaN means? Not a number. So we'll store them with NaN, and then we'll see where to go with them. So we imported NumPy, as NumPy is good at handling these values, and it provides direct methods to replace the values. So inspecting the missing values in the dataset, but what we are doing in this task is that ccapps.isNull.values.sum. So we are printing the sum of the number of values which are null in our ccapps dataset. So this is the output for this. 0th column has 12, first column has 12, second has 0, third has 6. So these are the number of missing values that we have in our dataset. Next, we'll replace the question marks with none, not a number. ccapps equals to ccapps.replace, what to replace and what to replace it with. So replace question mark with np.nan. Next, we'll again try to print the dataset, and we'll see if the question marks have already been replaced with nans. Next, total nan, string of ccapps.isNull.values.sum. Total nans, so look at it here. Okay, it didn't print. Yeah, here it is. So total nan is 67. So first of all, the nans we had were just a second. Okay, so here we replaced question marks with np.nans. So now total nans we have are 67. I'm sorry, this might be an output of after I had executed this replace thing. So that's why it is showing zero number of null values, because all of them have been replaced by nans. So here we have 67 nans total in this data set. NaN by column, we are now trying to print the NaN per column. So 0th column has 12, NaN's first has 12, second has 0, and this way. And now we are again printing the last 17 values just to see if the question marks are replaced. So see, the question marks have been replaced. Oops, I just selected again. No worries. Okay, handling the missing values part 2. Now we have replaced all the question marks with nans, and this is going to help us in the next missing value treatment that we are going to perform. Any guesses on what the next missing value treatment we are going to perform? Yes, you got it right. At least some of you got it right. It's mean imputation. So we are going to replace the nan values with the mean of their respective columns. So an important question that gets raised here is why we are giving so much importance to the missing values. Can't they just be ignored? Well, ignoring missing values can affect the performance on a machine learning model quite heavily. So, and there are some models which cannot handle missing values implicitly, such as LDA, linear discriminant analysis, or normal discriminant analysis, NDA. No, not non-disclosure agreement. Okay, so we're going to start with mean imputation. CCApps.fillNA. Fill NA means replace the NA entries with this value that we are going to give in these brackets. So CCApps.mean in place equals to true. In place true means replace the like store the new replaced values in the CCApps dataset only. If we don't write in place equals to true, then we'll have to provide another data frame which will store these newly imputed values. Now we'll count the number of NANs in our dataset to verify. So total NAN plus string, again the same thing, converted to string. CCApps.isNull.values.sum. So the sum of number of values, not the sum of number of values, basically the number of values which are null. Okay, so CCApps.isNull.sum, and this is what it outputs. So all our missing values have been taken care of. Now we are going to the part 3. So we have successfully taken care of the missing values present in the numerical columns. Now we still have some missing values to be imputed for columns, all these columns, because these are non-numeric. So we cannot impute the means for non-numeric values. So as you can see, all our integer based columns, which are 2, 7, 10, and I guess 14. All these didn't even had any missing values in the past, because the total NAN number remains the same. So these didn't have any missing values, and our mean imputation was of no use to these. So basically we did nothing, but we learned something, how to impute the mean. Now we are going to do something for the non-numerical data missing values. Now this is a different treatment. So what we can do is we can store the values which are most occurring in these columns. So we're going to impute these missing terms to the most frequent values as present in these respective columns. This is a good practice when it comes to imputing missing values for categorical data in general. Categorical data stands for the data that is not numerical and which is more category based. So basically class based, kind of which standard does your child reads in. So whether he's in 6th grade, 7th grade, 8th grade, all these are classes. So this is basically categorical data and not numerical data. So we'll iterate over each column of CCApps. So for call in CCApps, now we'll check if the data type is object. You might remember that .d types give us the object type of that specific column. Now CCApps equals to CCApps.fillNA. We'll fill NA in this, and you can see that we had to write CCApps equals to here. So I tried not to write in place equals to true in this, for you to get an idea of what is the difference in both of these methods. Now CCApps column dot value counts dot index 0, and so we imputed with the most frequent value. How we did that? So value counts. So this basically gives us an array in which the index 0 value is the one which occurred most frequently. The second one is the value which occurred second most frequently, and so on. So we are replacing this with the value counts index 0 value. That means the value which occurred most frequently in that particular column. Now we'll again count the number of NANs using the same method. So total missing values is 0 now. And all the columns have been set to 0, and all the missing values have been taken care of now. How we took care of the missing values? We replaced the mean value for the numerical columns, and we replaced the most occurring, most frequent term for the object type attributes. Now we are going to our next part, which is pre-processing the data, part 1. So But even after our missing values have successfully been handled, there are still some uh, minor but essential data processing things that are left before we proceed towards building our machine learning model. Now we are going to divide these remaining pre-processing steps into three main tasks. One, convert non-numeric data into numeric, split the data into train and test sets, and scale the feature values to a uniform range. Although this is pretty easy to understand, but I'll still go in detail. So convert the non-numerical data into numeric. We cannot handle the object type data. We want numeric data to for our machine learning model, and we'll also see that we do not need things like zip code. So zip code basically doesn't affect your credit card application as you might think of it. uh, Not zip code exactly, it might affect, but there are some things which do not affect our uh, credit card approval at all, but these are still in our data set. So one such example can be your father's name, for example. So we do not have to do we do not have to put your the father's name in consideration when we are looking at your credit card application and whether to approve it or reject. So these are some kind of features which need to be dropped. Okay, so these are main three main features. We'll split our data into train and test set, and we'll select the feature values. We'll scale the feature values to a uniform range. So there are some values which are ranging from 2 to 67, and there are some which are ranging from 1,500 to 1,600. So we want all of them to be scaled to a level, and most in most cases that scaling down is done in the interval 0 to 1. Okay, so first of all, we'll be converting all the non-numerical values into numeric ones. So we're doing this because not only it results in a faster computation, but also many machine learning models like the XGBoost, and especially the ones developed using scikit-learn, require the data to be strictly numeric format. So there's this technique called label encoding, and there's this amazing blog at scikit-learn.org which tells you what label encoding is. You should give it a read if you're new to label encoding, and if you have already done this, then this thing should not be new to you. So we'll import label encoder from sklearn.preprocessing import label encoder. LE is the object, is a variable we are storing label encoder object with. Now we'll iterate over all the columns, and if the data type is object, we are not dealing with any numerical data type here because we are converting the non-numerical data types into the numerical ones. So we have to specifically check if the data type is object first in the first place. Then we'll use label encoder.fit ccapps column, which column we want to fit, and so we are iterating over these columns, and the column will go here, and that column will now store le.transform ccapps column. So label encoder will use this function transform to transform our column ccapps call, and then we'll store this in the same variable. So this is same as saying in place equals to true. I think after so many references to in place equals to true, this should be very, very, very clear by now. Next, we'll go into ccapps.info and we'll see the information again. So we see here the D type for every column has been converted to int or float. The float ones remain the float and the other ones have been converted to int. Now we're splitting the data set into train and test sets. This is something which is very common and a basic step. So yeah, here we talk about the thing I was talking about earlier. Features like driver's license and zip code are not as important as the other features of the data set for predicting credit card approvals. So we should drop them, or we can assign them some weights. Weights or bias. So we are not going into that much detail, and we'll simply drop both of these features because we feel that these do not have any significance in this application process. Now, import train test split, sklearn.model selection, import train test split, ccapps equals to ccapps.drop 1113, access 1. What this means is we are dropping the features 11 and 13, that is dropping the columns 11 and 13, which are driver's license and zip code respectively. So we have dropped these, and what access equals to 1 means, we are not dropping the rows, rather we are dropping the columns. Now print ccapps.head, ccapps equals to ccapps.values. So this is the head printed here, and we'll segregate the features and labels into separate variables, x and y. Y is our target and x is the independent variable. So ccapps 012, ccapps 13, and we'll split it into train and test sets. This is something very common and all of us must be aware of this already. And y x train, x test, y train, y test. So these are the 4 segments of our data sets which have been separated now. So we'll train our model on the train data set segment, and we'll test it on the test data set segments. This is how our ccapps data frame looks like, since we did print ccapps.head. So this is the output. The next part of pre-processing the data is here. So the data is now split into 2 separate sets, train and test sets respectively, and we are left with one final pre-processing step of scaling before we can fit a machine learning model onto the data. What that step is, as we saw that earlier, here were our 3 main steps. So scale the features to a uniform range is the one which is left, the one which we are going to perform in this module. So there is a standard scaler in scikit-learn. What it does is it computes the mean and standard deviation on a training set, so as to be able to later reapply the same transformation on the testing set. And an alternative scaling technique is alternative standardization is basically scaling the features to lie between a given minimum and maximum value, which are often between 0 and 1, or so that the maximum absolute value of each feature is scaled to unit size. So for this we used min-max scaler, and for the second one we use max-app scaler. So here we are going to use min-max scaler, which is available in the pre-processing module of sklearn. So we'll import min-max scaler for that from there. We'll instantiate the min-max scaler and we'll input the feature range which we want, which is 0 to 1, and we'll store the rescaled x and rescaled y, rescaled x train and rescaled x test data by fitting both of them respectively. Now the final part, where we are going to develop a model for a machine learning model for our task. So we are going to use a logistic regression model, where we use logistic regression versus linear regression. This is a pretty basic thing. So in linear regression, the outcome or the dependent variable is continuous. It can have any one of the infinite number of possible values, and in logistic regression, the outcome or the dependent variable has only a limited number of possible values. So it should belong to a class. Here we have the target attribute, which is approval status. So we have to give the output. The output has to be one of the 2 available classes, which is yes or no. The application is approved or not. Not approved or not, basically will be approved or not according to our prediction. So we're going to use logistic regression here. Now, out of 690 instances, there are 383 applicants that got denied and 307 applications got approved. So there are percentages as well. 44.5% got approved and the rest got denied. This gives us a benchmark. So a good machine learning model should be able to accurately predict the status of applications with respect to these statistics. Now, which model should we pick? A question to ask is, are the features that affect this credit card approval decision process correlated with each other? Although we can measure the correlation that is outside the scope of this notebook, so we'll rely to our intuition that they indeed are correlated for now. Because of this correlation, we'll take advantage of the fact that generalized linear models, GLMs, perform well in these cases. Let's start our machine learning model building with a logistic regression model, which is also a generalized linear model. So we'll just import the linear regression from sklearn.linear model, and we'll instantiate the LR classifier with the parameter values, the default parameter values. So logreg equals to logistic regression. This is where we are instantiating it, and logreg.fit rescaled x train and y train. Now we are making predictions and evaluating the performance. How well does our model actually perform? Now we'll evaluate our model with the tests on the test set with respect to classification accuracy. We'll also take a look at the model's confusion matrix. Confusion matrix you must be aware of. So it basically stores false positives, false negatives, true positives, and true negatives, not in that order. Now, in the case of predicting credit card applications, it's equally important to see if our machine learning model is able to predict the approval status of the applications as denied that originally got denied, which is true positive. Now, true negative, I'm sorry. If our model is not performing well in this aspect, then this might end up as approving the application that should have been approved. Confusion matrix helps us to view our model's performance from these aspects. So we'll make the confusion matrix. sklearn.metrics import confusion matrix, and y prediction equals to logreg.predict rescale x test. So x test has been rescaled and stored into rescale x test variable, and then we'll predict based on the logistic regression model that we have trained just in the previous task. Predict the accuracy of logistic regression classifier. And how we'll predict the accuracy? We'll simply print the logreg.score, in which we'll input rescale x test, and y test. Now print the confusion matrix. So confusion matrix for y test and y prediction. So this is the confusion matrix which we have got. Confusion matrix basically is a 2x2 matrix which stores true positives, false negatives, and true negatives in this order. So our true positives, which are in the first quadrant, are 93. So 93 is a pretty good number. We have 93 true positives. We have 10 false positives. We have 27 false negatives, and we have 98 true negatives. So the accuracy of our logistic regression classifier comes out to be 83.77%, which is quite good since we're doing this for the first time and we do not even have a very elaborated data set. We just predicted it with 690 applications and we were able to perform this well. So this is quite an achievement. Clap for yourselves. And now grid searching and making the model perform better. This is out of our scope for this video. This is something we need to study before we dive directly into grid searching. And also I am quite hungry. Okay, thank you for being with me throughout this video, and I hope you like this. I hope you will make your own automatic credit card approval prediction machine. And yeah, thank you. Bye bye. Have a good day. Keep safe, wear masks, don't go out unnecessarily. Don't forget to pay your home staff. Okay, that's all. Thank you. Bye bye.